Can you guys see the drawing on the screen?
Yes.
All right, cool. All right, so I prepared 2 slides for the 2 review sessions. So today we're gonna go over the first 5 chapters, and tomorrow we go over the remaining 4 chapters. All right, so the way I'm gonna do the review is that for each chapter, I'm gonna do chapter by chapter. Right, so for each chapter, I'm gonna list the important bullet points, then using examples to cover those bullet points.
Gabby, please go. I know, right? I know.
All right, can you mute? Alright, cool. All right, so I'm gonna do chapter 10 and 11 together because they're closely related. Right, so chapter 10, basically the main idea is how to draw the Lewis structure for a molecule, and also based on the Lewis structure to predict the molecular structure of a molecule, right? So we did this a lot in lecture, also in the lab, and I think because you can find this anywhere on the internet also. So I think everybody should get 100% on this type of problems, right? So the bullet points including, right, so how to draw the Lewis structure, right? So remember the octet rule, right? So for the central atom, right, for the central atom in the first 3 periods, right, they obey the octet rule, right? And there are a few exceptions. For example, the elements in the column 3A, right? So they're called electron deficient. So they can have less than 8 electrons around them. And for the central elements that has a row number, right, higher than 3, they could have more than 8, right? So we did all those exceptions in the class, right? So another way to review this is go over your lab number 1, right? So all those different molecules, right, each represent a different molecular structure, right? Understand how you derive those molecular structure. And another thing is calculate the formal charge, right? So calculate the formal charge of any atom in the molecule or ion, right? So it's important because sometimes, right, we could end up with, for the same molecule, right, we could end up with different Lewis structures, but only one of them is most preferred, right? So being able to determine the formal charge will help us determine which structure is the most stable, right? So there are 3 rules, right? So first is we want most atoms to have a formal charge of 0, right? So the more 0, the better. And then second rule is that we don't want the same non-zero charge on the 2 atoms next to each other, right? The same charge repel each other. That's not preferred. And third rule is that we want the atom which is more electron negative, right? The more electron negative atom to have more negative charge, right? So if you have oxygen and chlorine, right? So and you have to have a -1 charge. So that -1 charge should be on oxygen, not chlorine, because oxygen is more electron negative. Right, so last thing is based on the electron negativity or predict the polarity, right? So this is determining the molecule is polar or non-polar. It's also going to be useful in chapter 12 when we try to determine the major intermolecular forces, right, between the molecules, right? So that is done based on the 3D structure, right, not the Lewis structure, right? So we're gonna go over some example of this. Right, so chapter 11, right? So mainly how we involve this molecular orbital theory, right? So the atomic orbital theory is hybridization, and also the molecular orbital theory, right? So all this is based on first we know how to draw the Lewis structure and the molecular structure, right? So that's why I put these two chapters together, right? For this hybridization, right? We should be able to tell what type of hybridization orbitals the central atom has, right? Based on the number of electron groups around the central atom, right? So single bond, double bond, triple bond, lone pair of electron, or a single electron, right? They all counted as an electron group, right? So we could have sp, sp2, right? sp3, right? So this is for one electron groups, right? Mean two electron groups, right? This is 3 electron groups. This is 4 electron groups. And something we didn't do in the exercise, and I don't ask you guys to draw, is those with the D involved there, sp3d, sp3d2, right? Those are with 5 or 6 electron groups around, and those only applied to the central atom which has the orbitals, right? So that means they must be like on the row 4 or even higher, right? So let's look at some examples, right? So first, this problem asks us what's the type of hybridization, right, for this structure, right? So for first one is carbonate, right? So remember, let's start by drawing the Lewis structure, right? So we start with central atom carbon, right? 3 oxygen. And so we count the total number of valence electrons, right? Carbon has 4, oxygen has 6. So the total, this is plus, sorry. So the total will be 22. But remember, for polyatomic ion, right, we also should consider the charge. So 2 more electrons, right, in this case. So the total will be 24 electrons, right? So we connect the central atom with the surrounding atoms. Right, first, we add the lone pairs on the surrounding atoms, so they obey the outside rule. And we see how many electrons we have left, right? So for each oxygen, we have 6, and there are 3 single bonds, so that's another 6. So we have 24, right? So now we have the correct number of electrons, but in this case, the carbon, right? The carbon doesn't obey the outside rule, but it's not one of the exception, right? So one of the single bond might become a double bond, right? Either this one or this one or this one, right? So to represent the resonance structure, they use this dotted line, right, to represent the resonance structure, right? So this meaning that this double bond could be between any oxygen with the carbon. And this is one of the carbonate resonance structure. Right, so to determine the formal charge, right, the equation is the number of valence electrons, right? For carbon here, it has 4 valence electrons, right? So we minus, right? So we minus the number of long electrons that not in the bond, right? So those are not involved in the bond. So here is 0, right? So here is 0. And then we also need to minus 1/2 of the number of the shared electrons. Right? So for this carbon, we have 1, 2, 3, 4 bonds, right? So 4 bonds is 8 electrons. Right? So for carbon, in this case, it has a formal charge of 0. Right? So for this oxygen, right, it's gonna be 6 minus 4. Right? We have 4 lone electrons, and also minus 1/2 times 4. Right, which is also equal to 0, right? So anytime you have a carbon oxygen double bond, right, that oxygen will have a formal charge of 0. And for these two oxygen, they're identical, right? So the formal charge will be 4 minus 6 minus 6, right? It has 3 lone pairs, so that's 6 unbonding electrons, and minus 1/2 times 2. And so that is -1, right? So each of them has a -1 formal charge. So overall, it has a -2 formal charge. All right, so every time you determine the formal charge, add them up, and that should be equal to the overall charge. Right, so now in terms of the type of hybridization, right? So carbon has 1, 2, 3, right? 3 electron groups around it. So this carbon is sp2 hybridized. Right. So for this carbon, right? So it has also 1, 2, 3, right? This is sp2 carbon, and this is also a sp2 carbon. Right. So for this single bond, this is overlap between end-to-end overlap, right? This is called sigma bond. Right. So within a pi bond, right? Within a double bond, right? One of them is a sigma bond, and one of them is a pi bond. Right. So remember the composition of multiple bonds, right? For triple bonds, it's 1 sigma bond and 2 pi bonds. Right. So for this oxygen here, right? So it's also sp2 hybridized. Right. It has a double bond, 2 lone pairs, so that's 3 electron groups. Right. And for this oxygen here, it's gonna be sp3, right? Because it has 3 lone pairs, 1 single bond, that's 4 electron groups, right? So that's sp3 hybridized. In this example, we have different chlorine oxides, right? So in this one, this is a special one. This belongs to one of the exception, right? We have odd number of electrons around the central atom, right? So to derive this structure, let's try it again, right? So we want chlorine and 2 oxygen, right? So overall, we should have 7 plus 6 times 2, which is 19 electrons. Right, so by adding the lone pairs on oxygen, right, so we have 6 times 2, right, plus this 4 from the single bond, which is 16. Right, so those, we have 3 electrons left, right? So those 3 electrons should be added to the central atom. Right, so only 1 pair and then a single electron, right? So that's where this 3 electrons come from. And we know this is not stable, right? Based on the outside rule, right? So this chlorine right now, right? So it only has 7 electrons around it. And also, if you just look at this structure, right? So the oxygen has a -1 formal charge, and the chlorine has a +2 formal charge, right? They have no non-zero charge. That's not what we want. So let's try to make the double bond, right? If we create 2 double bonds here, so the formal charge of oxygen will be 0, and so is the chlorine, right? So everything has a 0 formal charge. That's what we prefer. And so that's why we draw the structure this way. So in terms of the hybridization for chlorine, it has 2 double bond, that's 2 electron groups, 1 lone pairs, that's 3 electron groups. A single electron also counts as a electron group, so it has 1, 2, 3, 4. So chlorine is sp3 hybridized. And similarly for this, chlorine has 1, 2, 3, 4. So it also sp3, and this one is also sp3, right? So we count the number of electron groups around the central atom. Right, so if you wonder, right, where the double bond come from, right, try to draw the structure without the double bond and calculate the formal charge. You're gonna see those without the double bond are not stable, are not preferred by the formal charge rule, right? So that's why they have these double bonds, right, to have more 0 formal charges. And the last thing is the molecular orbital, right? So molecular orbital basically, right? So we when we combine, right, the atomic orbital of 2 atoms, right? So the overlap is a molecular orbital, right? So as I mentioned in the class, we'll only worry about those diatomic molecules, right? Those simple diatomic molecules in column 1, in row 1 and 2, right? So remember for the energy level, right? So we have a sigma 2s, sigma 2s star, right? So star is the anti-bonding orbital, right? So without the star, that's the bonding orbital. Each orbital can have at most 2 electrons, right? So the energy level right, which is on this axis. Right? So we should draw them from lower to higher energy level. Right? So for sigma, we can only have bonding and anti-bonding. But for pi orbital, right, for each type of pi orbital, we have two orbitals, right? Two pi bonding orbital and two anti-bonding orbitals. Okay. So for the first for the boron, carbon, and nitrogen, right? For their atomic molecule, because there's no or just one electron in the 2p orbital, right? That lower the energy state. So it involves some missing between the 2p orbital and the 2s orbital. So the sigma 2s orbital energy level is a little bit higher than the pi 2p orbital, right? So the only difference between the one on the right and the one on the left is that the order of the energy level between the sigma 2p and the pi 2p. Okay, so for oxygen, right, fluorine and the neon, we use the one on the left, and for the boron, carbon, and nitrogen, we use the one on the right. Right, so in this example, we want to draw the molecular orbital diagram for this oxygen, but with a -1 charge. Right, so remember the step is first we draw the electron in the atomic orbital first. Right, so for oxygen, we only worry about the valence electron. So oxygen is a second row, right, in column 6. So it has 2 electrons in the 2s orbital. Right, so for each of them, it has 2 electrons in the 2s orbital, and they have 1 in each 2p orbital, and the 6 electron goes here. Right, so that means for each oxygen, the first 2p orbital has 2 electrons, the other 2 has only 1. Right, so it's for this one. This is for O2. Right? So for O2 minus, that means there's 1 more electron coming in. Right? So give this a negative charge. Right? So you can add that extra electron in any of this second 2p orbital. So you say, let me add it here. Right, so we just then fill the electrons in the molecular orbital. Right, so for down here we have 4 electrons. Right, so we have 2 goes here, 2 goes here, and then on top we have 5 on the left, 4 on the right. So a total of 9 electrons to fill. So we just follow this order. Right, so we have 2 here and 4 here. So that's 6. Right, so 7. Right, remember we fill 1 in each orbital first and then start to pair them up. Right, so 1 more, it goes here. Right, so one of the pi 2p antibonding will have 2 electrons and the other one will only have 1. Right, so that's the molecular orbital diagram for this species. And for the configuration, right, so we use a parenthesis around each molecular orbital, and the number of electrons is as the superscript. Right, so for the same type of molecular orbital, for example, this pi 2p, you can also combine them. Instead of writing this twice, you can say pi 2p4. That's also fine. Okay, so in this case, you have same pi antibonding orbital, but they have different number of electrons in them. Right, this one has 2, this one has 1. So now you can also combine them to say pi 2p star 3. Right, so for people who understand this, they know, oh, that's gonna be 2 in one of the orbital and 1 in the other orbital. But to show this difference, it's better to separate them, right? So it's clearer for you, right? So next one is deciding the bond order, right? So remember, bond order is 1/2, right, times the number of electrons in the bonding orbital, right? Those without the star notation, right? Number of electrons in the bonding orbital minus the number of electrons in the anti-bonding orbital. Right, so in this case, we have 10 in the bonding, 7 in the anti-bonding. So the overall bond order is 1.5. Right, so to determine whether it's stable or not, as long as it's not 0, it is stable. Right, if it's 0, it's not stable. For example, like this diatomic, right, inert gases, they are unstable because their bond orders are 0. Okay, so as long as it's not 0, it is stable. And to determine whether it's a paramagnetic or diamagnetic, if you have one single electron in any of this molecular orbital, it will be paramagnetic. If all the electrons are paired up, that will be a diamagnetic. Okay, so for chapter 12, right? So we mainly focus on the heat of enthalpy, right? So this delta H, right, during a phase change, and also understand different type of intermolecular forces and determine what type of force between the compound and also how to compare them, right? How to rank them, right? Because different type of intermolecular forces have different strengths. Right, so in this chapter at the beginning, right, we work on the calculation of how to calculate this overall delta H change. And also this delta H is related for gas, right? For gas and the volatile liquids, right, is related to the vapor pressure, right? We can use this Clausius-Clapeyron equation, right, to calculate or to correlate the heat of vaporization to vapor pressure. Right, so also this is a 2-point version, right? So this is what we do in the lab, right? So if you know any of these 2 different temperatures, you know the heat of vaporization, you can predict the vapor pressure, right, at another temperature. Right, so if you may see any problem asking any of this, right, you can use this equation, right? If you know 4 of them, you can calculate the other one. And also know how to read a phase diagram. Right? So we're gonna do an example later. And then we've mentioned about hydrogen bonding, right? So how to draw hydrogen bonding, how to determine whether this molecules has a hydrogen bonding or not, right? Remember, we want them to have either oxygen, fluorine, or nitrogen, right? So these are the 3 electron negative atoms that the molecule should have. And the other atom must have this proton to bond to this electron negative atoms, right? So that's the prerequisite for the hydrogen bonding. And also the last one is determine the type and the relative strengths of different type of intermolecular forces. Right, so here this figure, this is called the CT curve, right? So the not the CT curve, the phase change curve, right? So when you heat or cooling a substance, right? So we have this change of temperature or at equilibrium stage, right? So at any of this stage, there is a heat involved, right? So we should be able to calculate the heat involved, right, during any segment of this phase change. And for the phase diagram, right, be sure you know how to read this. Right? There's some important points, right? Triple point, which means the coexistence of all these 3 physical states. Right, so every time you pass this borderline, right, so that means there's a phase change involved, and it happens at this corresponding temperature and pressure. And this is above this region is called a critical point, right? This is a super critical fluid. Right, so, and this table here on the right, give us this relative, so from top to bottom, right, the strength goes down, right, the strength goes down. So the important type of intermolecular forces are listed here, right? So when I give you any compound, you should be able to know which is the dominant form of the intermolecular force, right? So for a molecule, it could have more than one type of these bonds, but one of them will be dominant, right? The dominant one will be the one with the higher strength, right? Which is higher on this table, right? So let's work on a few examples. Right, so for this problem, we also did in class, right? So we have water, right? We're heating the water, right, from liquid to gas phase, right? It has from 85 Celsius to 117, right? So we know water boils at 100 Celsius. So we know when it's 85 Celsius, it is liquid. And then when it reaches 100, it has this equilibrium state where the temperature remains as 100. right? And then when it goes above, when all the water liquid molecule become gas, right, the temperature start to rise again. So the temperature start to increase, right? So we start with 85 all the way to 117. So we want to calculate the heat involved in this change of temperature, right? So we calculate each part, right? So we calculate the heat in each part. When there is a temperature change involved, right? So we use this equation, right? So number of moles or the amount, right, times the heat capacity times delta T, which is final minus initial temperature. Here about this amount and the heat capacity, you have to pay attention, right? So it depends on what the unit for C, right? So for the heat capacity, if the unit is given in joule per mole per Celsius, you have to convert the amount of the substance into number of moles, right? Just like in this case, we know the mass, but the units in moles per mole, so we have to convert the mass into a number of moles. Right? So then multiply this to cancel out this number of moles, because you eventually you want your heat only have the unit of joule or kilojoule, right? You don't want the other units in the final result, right? So sometimes the heat capacity is given in joule per gram, right? In joule per gram per Celsius, right? In that case, you don't have to convert the mass into mole anymore, right? If the mass is given, you can directly use it, right? So your overall role is cancel out the unit for the amount of the substance, also the temperature, right? You want to end up with joule or kilojoule, right? So stage 1 and stage 3 both have a temperature change involved, right? So we use a similar equation, but also pay attention, right? For different phases, for the same molecule at different phases, the heat capacity is different, right? So use the corresponding heat capacity, right, for each phase. And at equilibrium stage, right, because there is no temperature change, we use this equation, right? So the amount of substance times the heat of this phase change, right? So in this case, it's vaporization, so we use vaporization, right? So this value is given. Let's also pay attention to the units, right? In this delta H, the unit given in kilojoule per mole, right? So we want the unit in kilojoule, so we need to delete the mole. So you also need to convert the gram into a mole. And sometimes it's in kilojoule per gram. In that case, you don't have to do the conversion, right? So also you have to use the same unit for the energy, right? So you got joule in stage 1 and 3, but kilojoule in second stage, right? Make sure you use either joule or kilojoule, or if the question asks you use kilojoule only, you have to use kilojoule, right? So at the end, we just add them up. Right, so if this number given is a say is a condensation, right? So but you want vaporization, right? This is a negative of a delta H condensation, right? So basically you have the same magnitude but different sign. Okay. So this one we want to know the strongest intermolecular force in this compound. So this is a methanol, right? So methanol is basically CH3 and with OH attached, right? So first, we know that it doesn't have any metal ions involved, right? So there's no ion dipole, right, which is the strongest. The second strongest is the hydrogen bonding in that table, right? So this molecule, right, it has hydrogen bonding because if you draw another one, right, it has oxygen, right, which is one of those three that we want, and also it has hydrogen, right, attached to it. So the hydrogen bonding can be formed, right, between this oxygen and this hydrogen, right? So the answer should be B, hydrogen bonding, right? So dipole is also exists, right? Because this molecule is a polar molecule, right? So the polarity point this way, right? So this is a polar molecule. So dipole also exists. And the London dispersion force also exists between these molecules, right? So A, B, C, they all exist, right? But the strongest will be the hydrogen bonding, right? So dispersion not only exists in non-polar molecules, right? It also exists in polar molecules. Ionic bond force and the covalent bonds, they are called intramolecular force, right? So those are the force within the molecule, not between the molecules, right? So any bond here inside this molecule, that's covalent bond, right? So, but that's not the bond between the molecules. Right, so for this one, silica tetrachloride, right? So what force opposes the vaporization of this compound? Meaning that what type of intermolecular force are holding these molecules together, right? So for this one, we must know how to draw the structure, right? So this basically same as methane, right? So silica, right? On periodic table, silica is below methane, right? So we know methane is the most typical tetrahedral structure, right? So one of them is dashed, one of them is the wedge, right? So it has this perfect tetrahedral structure. We know that if it has same four surrounding atom, it is a nonpolar, right? It is a nonpolar molecule, right? So nonpolar molecule, the London dispersion force will be the only intermolecular force, right? So same for this silica tetrachloride, right? So it is also a perfect tetrahedral structure. So this London dispersion force is the only force holding the molecules together. So the answer should be A. And at the end of this chapter, we also talk about the three phenomena, right? First, it's called surface tension, right? So the surface tension is actually due to the intermolecular force of these liquid molecules, right? So to be able to break through this surface, right, the force generated must be higher than this molecular force, right, or this surface tension. And also the viscosity, right, so how sticky this liquid is, and that's also related to the intermolecular force. Right, so know how to compare this different type of characteristic of liquids. And then the last one is the capillary force, right? So we have different scenarios, right? For water in a glass tube, right? We have this concave surface because there's a intermolecular force between the water molecule and the silica dioxide, right? So on the inner wall, right, on the surface here, right? The adhesive force, right, is stronger than this intermolecular force in the water, right? So the water molecules on the inner wall, they just hang on there, right? So that's why you see this concave. And for mercury, right? Mercury, the top, they have this metal atoms, right? The cohesive force is stronger than the this adhesive force. So you see this surface, right? Vertex surface. So chapter 16, we deal with reaction rate. So we mainly talk the reaction rate or the rate constant. Right? So the K is the rate constant. Right? So remember, this rate is the representation of how fast the reaction proceeds, not how much, or not the extent of the reaction. Right? The extent depends on equilibrium, which is we will talk about in chapter 17. Right? So this reaction rate depends on how fast the reaction proceeds. Right? So the higher the temperature, the faster the reaction. And we also did in lab, I think number 6, I think, we determined the reaction rate for a chemical reaction between iron and cyanide, right? So not cyanide, ICN, right? So remember we did this in the lab, right? So to determine the reaction rate, right? So this is a fake blood. Right, so for this chapter, right, reviewing that lab is also gonna be helpful. Right? FeSCN2+. Right, so in this lab, in this chapter, right, so first we need to know how to determine the rate of a reaction. Right, for example, if your reaction has a general form like this, and each reactant product has this coefficient, right? For the reactant, is you're gonna have a negative sign. Right? And then 1 over the coefficient multiply the change of concentration divided by the reaction time. Right, so same for the other reactant, but for the product, you don't have a negative sign, right? So for the reactant, you're consuming it, so the rate has a negative sign. But for the product, you're producing it, so it doesn't have a negative sign. Right, so this is basically how we determine the rate, right, based on the change of concentration over time. And if we can control the experiment, right, by keeping one of the reactant concentration same, but the other one different, we can actually determine the reaction order of each reactant, right? So this is a general form for this of this is called rate law equation, right? So this is a rate law equation for this reaction. Right, so for the rate law reaction expression, right, has nothing to do with the coefficient. This m and n is called the reaction order. Right? So m is with respect to A, n is with respect to B, and the m plus n is the reaction order for the overall reaction. Right. So if we know the concentration, we know the reaction, determine the reaction order, and then we can calculate the reaction rate, we can determine the rate constant. Remember, we did this a lot, right? So we have a experiment 1, 2, 3, 4. We pick 2 experiments, right? Divide them up, and so to determine the reaction order for each reactant. And the last one is the Arrhenius equation, right? So which relates the rate constant to the activation energy, right, of the reaction, right, at different temperatures, right? So another important thing in this chapter is the different reaction order, right? So we talk about 0 order reaction, first order, second order, or even third order of a reaction, right? Those are the most common reaction orders we've seen. Right? So different reaction orders, they have a different units, right? They have different units for this rate constant K. Right? So when the rate constant is given, you can simply base on the unit of the rate constant to determine the reaction order. Right? So the general formula of the unit for a reaction order is this like this. Right? So using this table, right, this is a good helper. Right? If you see this reaction order, a rate constant with this any of this unit, you can determine the reaction order right away. And another thing is half-life, right? So half-life is for the concentration, right, of a reactant to become 1/2 of the original concentration. Right? So that's the definition for the half-time. So let's work. Oh, there's another slide. Right. So this table, right? So I think I also put this in the equation sheet for our second exam. Right. So you can use this table, right? So do the calculations, right? The equation to determine the half-life. And also this linearized or called integrated rate law equation. Right. So you see for different reaction orders, right? Their forms are different, but they all contain the same variables, right? Final concentration, initial concentration, rate constant, and the time, right? So for these 4 variables, if you know only 3, you can calculate the other one. Right? So sometimes the question doesn't tell you which reaction order it is. You don't know which reaction to use, but just pay attention to the unit, right? Just pay attention to the unit of this K value, and then decide which equation to use. Right, so first, let's work on example of how to determine the reaction order. Right, so we have this reaction, right? So ABC generating D, and we done 4 experiments, right? So because we know that the general form for this reaction will be, right? So rate equal to K times the concentration of the 3 reactants, and each of them will have a reaction order, right? M, N, I say the last one is P, right? So this will be A, B, C, right? So we have 3 reactants, right? So that's A, B, C, right? So we want to determine M, N, and the P. Okay, so first to determine the M, right, we pick experiment 1 and 2, right? Because in this experiment, the concentration of A is different, but B and C are the same, right? So for reaction experiment 2, right? So the rate will be equal to K times 0.1 to the M, right, times B to the and C to the P. Right, so this is for the experiment number 2. For experiment number 1, it's same K, but we have a different concentration, right? 0.05 for A. And the B and the C are the same. Right, so we can divide these two equations. So B and the C, they all cancel out. Right, the K cancel out. Right, so here, this is the rate. Right, so the rate for reaction 2 is this number. Right, so the rate for reaction 1 is this number. Right. So eventually we have, right, this 0.1 over 0.05 to the M equal to the ratio of the rate. So then we can take the log of each side and determine the exponent, which is the reaction order. Right, so to determine the reaction order for B, right, so we want to pick two experiment that has the different concentration of B, but same concentration for A and C, right? So that's gonna be reaction 2 and 3, right? So we're just doing the same thing, right, to determine the reaction order for B, and same for C, right? So we've done this so many times, right? So we should be able to know how to do this. Right? Refer to the practice exam and also the homework. And so after we determine the reaction order for each reactant, right? So what we have is, right, so A has order of 1, B has order of 2, C has an order of 3, right? So for zero order, we don't need to represent them in our rate law expression, right? So overall, we can just say K times A times B squared, right? So this is 1 plus 2 is 3, right? So that is third order reaction, right? So for third order reaction, this rate constant here, it should have this unit, right? So your result should have this unit. And then you can pick any experiment, right? So after you got this exponents, right, you can pick any of this experiment using that reaction rate and the concentration, right, to calculate this rate constant. And for this problem, we have this reaction, and we know this second order reaction, right, because that's a 2 here. So this is a rate law expression, and the unit also is given, right? So you see this unit matches the second order reaction, right? So we know for second order reaction, we want to use this equation, right? So we want to use this equation. So this is again this from the table, right? The linearized or integrated rate law equation, right? So in this question, we know the initial concentration is 1.5, and it asks us how long does it take for the concentration to reach 1/3. 1/3 of the initial concentration will be 1.5 times 1/3, which is 0.5. Right, so here the final concentration will be 0.5. The initial concentration will be 0.5. The K value is given, right? So we can calculate T. Right, so we got 7 seconds. Right, so the other part of the problem asks us what's the concentration of this AB, which is the reactant, after 10 seconds. Right, so in this case, we don't know the final concentration, but we know the initial concentration is 1.5. We know the K value, and we know the time, reaction time 10 seconds. So we can calculate the final concentration. Right, so again, first, based on the unit of the rate constant, right, determine which linearized equation to use, right? No matter which form it contains these 4 different variables, and normally the question will give you 3 and ask for the other one. All right, that does become a simple math. So for chapter 17, we talk about the reaction equilibrium or the extent of a chemical reaction. Right? So this is different than the reaction rate. Right? So in this chapter, we want to see, right, how complete the reaction can proceed, and we introduce this definition called the reaction equilibrium. Right? And then we have this equilibrium constant K. Right? So this equilibrium constant K is an indication of how much this reaction can proceed, right, from the reaction side to the product side, or the extent of the reaction, right? If you see numbers, right, large numbers, K values, that means this reaction is preferred to the right, or the equilibrium precision is very close to the side of product. If you see an equilibrium constant that has a very small number, right, 10 to the negative 3, 4, or even lower, that means this reaction doesn't want to proceed. Right, so the equilibrium precision will close to the side of the reactants. Right, to determine, right, every time you have a mixture of a reactant or reactants and the products, right, so you want to determine whether the system is at equilibrium or not. If not, which direction this reaction will proceed. Right, so we're gonna compare this reaction quotient Q. Right, we're gonna compare this Q with the K value. Right, so for a general chemical equation with coefficients, right? So we have this expression, right? So Q is the reaction quotient, C, the subscript C is the concentration based. In your textbook, also pressure based, but we never talk about that, so you don't have to worry about it. Right, so the coefficient, right, become the order of the reactant and the product, right? So that becomes the superscript. Right? When we determine the rate constant in the previous chapter, right, this coefficient doesn't play any role. Right? But for equilibrium or the reaction quotient, this coefficient will be important. Right? So the higher the coefficient, the higher the order for the reactant or the product. Right? So when we have a mixture of these reactants and the products with known concentrations, all we need to do is write this concentrations in this form of QC and get a value, and then compare this value with this KC value. Right, so if the Q is, right, greater than KC, that means we have too much products than the reactants, right, compared to the equilibrium condition. That means more products will react back into the reactant. So the reaction will be shifted to the left, right, until it reaches the equilibrium. When we have a QC less than KC, right, that means the reaction is not completed yet, or it haven't reached the equilibrium yet. Right? So the more reactants will react and produce more products, right, until it reach the equilibrium. So we have a shift to the right, right? So we have a direction will proceed to the right. So when the QC and the KC are equal, right, that means the reaction is at equilibrium, right? At equilibrium, it means the forward rate, right? So the rate forward and the reverse rate, right? They have the same rate, right? So meaning that the amount of the product generated is equal to the amount of the reactant, right? So in that case, we cannot say that reaction has stopped, right? It doesn't stop. It just means the amount of the reactant being produced is the same of amount of the reactant being produced. Right? So there's still reaction going on. Right? So for the Q and the K value, right? If we reverse this reaction, right? So we take 1 over the Q or 1 over the K. Right? For example, this reaction becomes C and D, generate A and B. We're gonna take 1 over of the Q and the C value, right? And if you change the coefficient, right? For example, if you multiply all the coefficient by a factor of n, you're gonna put this n as the exponent, right? So this k will become k to the exponent of n, right? So when they have to, this will become useful, right? When they have to combine 2 or more reactions, right, to generate and want to know the k or q for the overall reaction, and we should know how to, right, adjust this k value based on what we did to the reaction. Right, so another important concept we learned is this the Chatelier principle. Right, so this is related to the shift of the equilibrium position. Right, so meaning that when you have a equilibrium condition and then you disturb, right, and you disturb this equilibrium condition by either, right, changing the concentration or changing the pressure when there's gas involved, right? Normally there's a gas involved for this, or also change the temperature when there is a delta H involved, right? So the equilibrium position of the reaction will be changed, and among all these 3 factors, only a change of temperature will change the value of K, right? So only the change of temperature will change the equilibrium constant, right? The other 2 will not change the equilibrium constant. All right, so there will be questions like what's gonna happen to the reaction, right? Or how the reaction is gonna be shifted, right? If you change one of these conditions, right? So the rule is that when this new equilibrium is re-established, right? So this reaction or this change, right? So this change happened between this old and the new equilibrium condition is called the net reaction, right? So it's called the net reaction. So if the equilibrium position shift to the right, right? So the reaction shift to the right, that means the net reaction, right, proceed to the right, or the other way, right? If it is shift to the left, that means the net reaction shift to the left, right? So this net reaction happens, right? It happens in the purpose that it's gonna decrease, right, the result caused by this disturbance, right? So for example, if you have a reaction A to B, which is at equilibrium, and if you add more A, right? So by adding more A into the reactant, that means you're increasing the concentration of A, right? So this net reaction will decrease that effect, which will decrease the amount of A that being increased. So that means more of the A will be reacted into B, right? So this reaction will proceed, right, to the right to reduce this increase of concentration of A. Right, so you should be able to tell, right, so the direction of this net reaction, right, when any of this change happens. Right, so another equation involving calculation is, right, so we mentioned that when there's a change of temperature, the equilibrium constant changes. Right, so we have this one-half equation, right, which correlates the K value to the delta H of the reaction. Right, so earlier you saw the Clausius-Clapeyron equation, right, which relates the partial pressure with heat of vaporization. And in last chapter, we have a rate constant, lowercase k, right, rate constant with activation energy. Right, so in this chapter, we have this equilibrium constant, this capitalized K with the delta H of the reaction. Right, so they are in the same format, right, but just different variables. Right, so let's work on this example. Right, so the question asks what happens. It's blocked here. So let's see. It asks us what happens, right, if we make these changes. which change will form, right? More calcium carbonate. Right, so, oh, is it stopped? So right, so A, we have a decreased temperature, right? So in that case, we're gonna look at the sign of delta H, right? So the delta H is a negative, meaning that this is a isothermic reaction, right? So for isothermic reaction, right, that means the heat, right? The heat is on the right hand side, right, on the side of products. So decreasing the temperature will cause a shift to the right. Right? So when you have a shift to the right, more calcium carbonate will be generated. Right? So that's for A. And for B, as increasing the volume at a constant temperature. Right? So when we have a change in volume, we want to look at the gas phase. Right? So this change of volume or pressure only impact the reaction that has a gas phase involved. Right? So in this equation, we have carbon dioxide on the left-hand side, but no gas on the right-hand side. Right? So we have the total number of coefficient of 1, right, for the left-hand side, 0 on the right-hand side. Right? So that means if we increase the volume, right, we have more room, right? We have more room for these gas molecules. So increasing the volume, the reaction will be shifted to the the side has a higher total number of coefficient for the gas phase molecules. Right? So that means, right, that reaction, right, for B will shift to the left, right? Because on the left-hand side, we have 1, right, which is higher than 0. Okay, so on the other hand, if we decrease the volume, the reaction will be shifted to the right. Okay, so in this case, when the reaction shifts to the left, that means we need to consume some of the calcium carbonate, right? So the amount will decrease. Right, so for C, we are increasing the partial pressure. Right, so again, based on ideal gas law, right, PV equal nRT. Right? So increasing the partial pressure, right? So also means lower the volume, right? Or another way you can think about it, because partial pressure, right, of carbon dioxide, right, is the based on the mole fraction, right? Based on the mole fraction. Right, so if there are any other gases involved, and then you increase the partial pressure, that increase the mole fraction. Right, so you have more. That means you have more carbon dioxide involved, right? So in that case, the reaction will be shift to the right. Right? If you increase the pressure, that means you lower the volume, right? So you lower the volume. This side you have 1 for the gas. This side you have 0. So the reaction also gonna shift to the right. So you're gonna have more calcium carbonate. Right, so last one is remove half of the initial calcium carbonate. Right, so remember when we change the amount of a pure liquid or a solid, right, they don't appear in the expression for the equilibrium constant or the Q, right? Because for this physical states, they don't appear in the expression, right? So for this reaction, we have liquid and the solid, right, on the right hand side. So it has nothing on top. On the left, we have solid and the gas. So the only thing we worry about is the carbon dioxide concentration. So even they change the amount of this solid, it doesn't affect this Q or K, right? So it has no change. This is the last problem for this session, right? So we want to be able to calculate the equilibrium concentration, right? When we have a mixture of a reactant or products using the ICE table. Right? So the ICE table. Right? So based on the initial concentration of each reactant and product, the change of concentration to get the equilibrium concentration, and then solve based on the given Kc value, solve for the unknown change of concentration. Right? So in this example, we have this compound, right? So we decompose into two different gases, right? We know the initial amount is 7.8 gram. We know the Kc value, and we know the volume, right? So we want to know what's the total pressure at equilibrium, right? So to know the total pressure at the equilibrium, we must know the concentration or the number of moles, right? So because the pressure depends on the number of moles, temperature, and the volume, right? So here we already know the volume, we already know the temperature, R is a constant. So we must know the number of moles, right? We must know the number of moles. Or if we do N divided by V, this is concentration, right? N over V is actually the concentration, right? Because that's mole per liter, right? So that is actually concentration, right? So that means if we have the total concentration of these gases at the equilibrium condition, we can calculate the total pressure, right? So we have this initial amount, which is in gram, right? So, but we want the concentration, right? So what you can do is convert the gram, right? You want to convert the gram by divided by its molar mass. I don't have it with me right now. So mass divided by molar mass, you get the number of moles. And then you know the volume, right? So then you use the number of moles, right, to divide it by the volume, right, to get the concentration. Right, so initial here, you can put concentration here. Right? So here, instead of using this, right, you also use concentration. But that is, you can do that or not because this is a solid. Right? So this is a solid. So if it's a gas, right? If a gas or aqueous phase, you have to convert the units into concentration if it is not given in concentration. But if it's a solid or liquid, because it's not involved in this expression for K, right? So you don't have to do the conversion, right? So the change, right? So we have no product at the beginning. So for the change, we increase 2x for ammonia, right? Because the coefficient of 2, so you have a plus 2x. And for carbon dioxide, it's plus x, right? So this is the expression for Kc for this reaction, right? So you will know the Kc value, right? So that's equal to 2x squared times x. This is actually 4x squared times x, right? That is 4x cubed, right? So 4x cubed is equal to this number. And make sure you know how to solve this on a calculator, right? When I grade the lab final, some of you don't know how to solve this. Right? So get a scientific calculator or use a calculator on the internet. Right? Make sure you know how to solve this. So after you solve this, x equal to this, right? So that means at equilibrium, the ammonia concentration is 2 times this. The concentration for carbon dioxide is 1 times this. So that this is the total concentration. So this total concentration is equal to N over V. Right? So that's N over V. So you times R, you times T, convert T into Kelvin. Right? So this is the total temperature. Right? So the main idea is know how to use this ICE table. All right. So if it's any reactant product is a solid and liquid, don't worry about the change. Right? So because it's not involved in the expression for the Kc. Right. So don't forget the coefficient. Right. So the change of concentration need to come with this coefficient. Right. And don't forget this exponent. Right. This exponent. If it's 2x, that's gonna be 2x the square, right? The square is also the coefficient. Right? In exam 3, some of you forgot to put the exponent during the calculation. Right? Got the wrong result. Right, so that's it for today, and tomorrow we're gonna do the remaining of the chapters. And if you have any questions, you can stay.
I have a quick question about submitting the final. So is it all right if we take pictures with our phone and then put those onto a Word document?
Yes, like for example, like some students do not have a printer at home, so like you can write your answers on papers, and you take multiple pictures, right? So I want you to put all those pictures in a Word file and then upload it, because sometimes I have students upload this format pictures that I could not open on my computer. Right. So, but if you put it in the Word, I can see it, or you can convert that Word into PDF. That's also fine. But what I do not want is you send me 10 pictures, and and they never name the picture. I have to determine which one comes first. That I have to grade like 50 exams, so I don't have time for those. So I hope you can put everything. Like if you prefer to print it out, write, and scan, that's perfect. But if you do take pictures of individual pages, please put them all in one file.
Yep. Thank you.
I think there was an interruption in between. I'm not sure whether the video is gonna be complete. If not, I'm gonna do another one and post it on YouTube. Right, so tomorrow we're gonna talk about chapter 18, 19, 20, and 21. And the exam, I think it's 50%, maybe 45% will be on the last 2 chapters, and the rest will be on the previous chapters.
Thank you, Dr. Zhang.
And for those of you who come in late, if you have questions, you can ask me. I will post the PowerPoint also on Moodle, and also the video on YouTube.
Okay, thank you.
I hope the video is complete. And do not drink disinfectant products. Oh my god. You guys watch the news about there are actually people drinking that? I think that's it. All right. Any question about homework for the last 2 chapters? Any problem in the practice exam? You will come to stay. We can work on those. Jasmine, you good?